Is it better now?
Yes.
Great, thank you. Sorry, I forgot to put on the mic. So the title is, as Greg just said, but I recently learned this word from cluster community. The word is trypophobia, and I quote: "This is a phobia, really, which is an aversion of the sight of clusters of small holes." So let me start with the bad news. So, well, kind of the term was coined in 2005. So only 5 years after the cluster algebras were introduced. Well, second, and understanding is limited, as Wikipedia says. And finally, unfortunately, there's no known treatment. So I'll try to make it a little better, but I'm not sure if I will succeed. So it's all kind of based on joint discussions with Gus Schrader. Discussions and works with Gus Schrader. And well, kind of on a slightly more serious note, what I wanted to discuss is, so when you talk about higher Teichmuller theory, sometimes you need to, well, the natural question is what happens when you cut a surface, and the question is basically how to cut a surface in a responsible way. So, and the answer will be basically that when you cut a surface, you create two punctures, and these punctures, they don't capture the new punctures and cluster structure around them. They don't capture what you had on the uncut surface. And so to fix that, you just need to modify a Fock-Goncharov recipe for the cluster structure on the surface just a little bit and throw in some frozen variables around those newly created punctures. And that would be the punchline. But now let me kind of try to say something more structured. So let me really briefly remind what higher Teichmuller theory does. According to Fock-Goncharov. So we have an S, it's a surface. We've seen that a few times this week. So it's a surface with punctures. And possible with boundary, and each boundary component of S has at least one mark point. All right, so that's one piece of the data we need for the Teichmuller theory. So another one is, sorry, board talks are hard. So another one, G, is a simple Lie group, and the Sky GS, it's a moduli space of the so-called decorated geolocal systems on S. So I will not really explain the word decorated, but instead I'll just quote a theorem due to Fock-Goncharov, Goncharov-Shen, and Shen. So it's kind of combination of the results. So just leave them with Fock, Goncharov, Shen. And the theorem says that, well, for a small print, a 4-dimensional 2 locus of, well, that guy X GS is a cluster Poisson variety. And again, once again, a small print when G is connected group of a joint type. But once again, the moral is that that guy is a cluster Poisson variety, and let me just give an example, and it will be running example for my talk, how you construct this cluster structure. Again, we've seen it 1,000 times, even this week. So you say this is your surface, so it's a cylinder, two boundary components, one more point on each side. The group is PGL2. Then you can think of the cylinder as just square with identified sides. So you can draw a diagonal, and then you triangulate the surface, and then in each in each triangle you put this kind of standard PGL2 type cluster configuration, cluster quiver, and then you glue these quivers together, right? So if you identify the two sides, the quiver that you get eventually will be that guy over here. Sorry? Complement. Sorry, yeah, complement of, yeah. Sorry, thanks. Complement. Thank you. Right. Right. Now there's sort of there's a quantization to this story. Let me briefly remind what quantization does. So quantization well basically does the following, right? So again, this is due to Fock-Goncharov, at least for PGLN case, that I would like to replace this algebra function, global algebra functions on my cluster Poisson variety, on my complement of convention to locus of the moduli space. So this algebra functions is clearly just the same as the global algebra functions on the cluster variety because they coincide up to codimension 2. And I quantize that guy, right? So I replace that quantum, that cluster Poisson algebra by quantum cluster algebra. So this is quantum cluster algebra. And what it entails in particular is that, well, if you had cluster coordinates y1 and y2, and they had a their Poisson bracket was some constant epsilon, sorry, epsilon times y1 times 1 y2, that quantizes to generators y1 y2 being q to the power minus 2 epsilon y2 y1, right? So these are now generators of a quantum cluster of this algebra. Okay. Now what quantum Teichmuller theory does, it starts with a group on the surface as the usual Teichmuller theory and produces you the following data. So it produces you an algebra and a representation, let's call it P, of this algebra. Now it actually also produces compatible actions of the mapping class group of the surface on both the algebra and representation. And arguably, that's the most important part, but I'll suppress that. I'll skip discussing. I won't discuss the mapping class group today. Right, so let's see an example how that works and what kind of representation we get. So we have our favorite quiver over there, at least favorite for today. So we have 4 generators. Let's call it this y1, y2, y3, and y4. And then I would like to make them act somehow on some space. It will be space of functions. So let me just set y1 to act by some operator x, y4 to act by operator p, y3 to act by operator p, y2 to act by operator q square p to the minus 2x inverse. And this, of course, is pretty arbitrary, but let me now try to say what are these operators. So here x stands for e to the 2 pi b x lowercase. 2 pi b is a constant, disregard that for now. P stands for e to the 2 pi b v lowercase. P lowercase is 1 over 2 pi I d over dx. Okay, now at least we see that we have one operator is multiplication by x and another is shift. And we finally set q to be e to the pi I b square. And then indeed, if this is the case, then we can see that px equals q to the minus 2 xp. So at least the commutation relations between the images of these cluster variables between these operators are as claimed. They q commute, and the exponents of q are given by these by the arrows of the quiver. All right. Now, what's the space of this representation? Well, sorry, our algebra L GSQ acts on representation P, which is some subset inside L2 functions of this variable x. And once again, the uppercase x acts by multiplication operator. And oh, sorry, like sorry. All right. Can I lower it again? Yeah. Can I lower this one a little? Yeah. Okay. Good. Yeah. Thanks. All right. So we act on some subspace of L2 functions of x. I won't discuss the subspace because, well, to actually make a honest statement, you need to discuss some function analysis, which I don't want. Just let me fix that. X is multiplication operator, and P is shift operator. Now, what just happened over here, right? So none of these cluster variables are really elements of my global algebra functions because they're x variables. When they mutate, each of the variable is not Laurent, right? So really, so elements of these global algebra functions, there were some combinations of this variables over here, right? So what really happened is the following: we started with some algebra that we were interested in. We embedded it into some quantum cluster. So this guy here is a quantum cluster. In other words, so it's quantization of a chart on our variety. So it's a localization of our algebra. And now made this guy act on endomorphisms of made this guy act on some representation. So sent it to endomorphisms of some representation. We could as well embed it into a different cluster. And these two are related by, say, mutation at variable yi. And again, write a similar representation. Right? And the statement, the some theorem that Fock-Goncharov proved is that you actually have an operator which gives you an equivalence between these two representations. So this is by q, this is by q prime. Which is a conjugation by some special function called quantum dialogograph. So in other words, to give a representation of this algebra, I first embed it into some cluster, pick some polarization, so pick some way with that cluster x variables act by multiplication of shift operators. And then if I go to a different cluster and produce a representation in a similar fashion, these two representations are related by certain operation, right? And when B is real, we have that those representations. So this action by phi of yi is a unitary equivalence between these representations. In other words, we have a kind of infinite family of unitary equivalent representations. And to go from one to another, we just do a cluster mutation. And now the question is, what happens when we cut our surface? And what is even expected to happen, right? So let's see an example. So here's the surface we started from. And let's say we want to cut it along this cycle over here. What we'll get is just two surfaces with these small cuts. So these are punctures here. And if starting from this surface S prime, you try to construct the same algebra, you'll see that the algebra LGS prime has center, and an element of the center is trace of the holonomy around puncture. Right? So conjecture, it's conjecture of Fock-Goncharov, is that if you start with the representation P constructed from your group and the surface, then this representation can be decomposed as some direct integral of representation P G S prime lambda. Lambda here is central character, so lambda tells you how center of the algebra LGS prime acts d lambda. Okay? And this is the composition as LGS prime modules. So implicitly here, I'm saying that you have an action of the algebra from the cut surface on both representations, and this is the decomposition. Right? And now let's try to understand how this works. And to understand that, I would like to look at some specific elements of our algebras and see what happens with them as we cut the surface. So let's try to do that. How much time do I have?
Oh, I would say still about like 13 minutes or so.
Ah, wonderful. Great. Thank you. Okay. So let's do examples of elements of L, G, S, Q, right? Well, once again, this is our surface. And remember what we did, we considered geolocal systems on this surface. And therefore, we can just look at different arcs or different elements of the so-called stated skein algebra and look at their, well, again, matrix elements and traces. So let me use different colors, right? So you can take the yellow holonomy, you can take the red one, or you can take the green one. Let me draw that. Let's see if it will be visible. Right? So as you can see, the red and the green, they're based on, they start and end on the boundary of the surface. So whenever you write a kind of parallel transport matrix, each of the matrix elements of this matrix, they will be actually elements of our algebra over here. But if we look at the yellow cycle, then this one is defined only up to conjugation by G, right? So only the trace of that yellow holonomy will be an element of our algebra LGS, right? So let's try to write some of these elements, right? So once again, yeah. So red one, let's call it M. Green one is N, and yellow one is L. Right. So L, M, N are holonomies, and then matrix elements of M and N lie in our algebra, and trace of L also lies in our algebra. Right. So let's calculate this guy N, and I try to do some preparatory work over here. Sorry for my board work. All right. So what we see over here is just this our cylinder kind of unrolled, at least, well, kind of unrolled twice. Well, you will see two fundamental domains on the universal cover of the cylinder, and the green holonomy N should go somehow from, well, let me just draw that, from here to here, right? Right. So and the way that we write this matrix, what we do is the following. We draw a kind of dual black-white graph, which I've drawn in yellow. The dual graph to the cluster quiver, and then so you see the pattern in each triangle. So you have three white dots, one black one, right? They're connected. And then I want my holonomy to exit through kind of this side over here. So I orient the two yellow arrows downward. And then I have a rule that if I have an unfilled arrow, I have just one outgoing arrow, and I have a field vertex, I have just one incoming, right? Using this rule, I can just orient the rest of the picture, get the so-called network. And so on. Now if now I can do the what is called a measurement matrix, right? So I have two arrows through which I can exit, and two arrows through which I can enter. And I just calculate. So I write the matrix. So ij element of the matrix will be, as usual, just a sum of all paths from ith entry to jth exit, and I just take the weight of this path. So let's do an example. Here I just redrawn this part of the network that was of interest to us, and so our matrix n will be, let's calculate. So from 1 to 1 we have just one path, and the weight of the path is everything below that. So here we'll have y1, y2, y4 squared. From 2 to 2 we have just one path, nothing below, so we write 1. From 2 to 1 there are no paths at all, and from 1 to 2 the path is y4 plus y1, y4 plus y1, y2, y4. Right? And then since this matrix, since the determinant of this matrix is not 1, we divide by the square root of the determinant. So divide by square root of y1, y2, y4. All right. Now we can ask ourselves, what is this matrix? What are the elements of this matrix in the representation? So if we set all the y's to be those x's and p's, those shift and the multiplication operators, what will happen in the representation? In the representation, this matrix will become the following. It will become 1 H01, where where H is the following operator: P plus P inverse plus QPX. Right? I just calculated. So elements of these matrices are all elements of my algebra LGSQ, and now I calculate those elements, how they act in a representation. Okay. Now, something similar happens to matrix M, happens for M, or can be calculated for M. And if we try to calculate the trace of our holonomy, we actually realize that this trace is actually equals to that one-to entry of our matrix in a representation. All right. Now, what happens when we want to cut this thing? So when we cut the surface, cut along the cycle L, well, in this surface, we just had some element of our algebra, which was not central. And now so it was some non-trivial operator, but now in the cut surface, our holonomy L should be holonomy around the puncture, and that should be the center. So when we cut, we should just diagonalize this operator. And so cut along L is the same as diagonalizing this operator H, right? And indeed, this can be done. So one can write a function depending on two variables, lambda and x, such that H applied to this function, psi lambda x, is lambda plus lambda inverse psi lambda of x. So this guy is an eigenfunction for H, and this is the eigenvalue. Right? All right, but then as we cut, we can ask ourselves, okay, so now we know what happens with one element of our algebra. What happens with all the others? So what happens with matrix n, say and m. Well, let's make a guess. So if indeed, wait, do I have a? So if indeed this construction should somehow respect cutting, then well, we see that the holonomy written drawn in green, this matrix n, well, cutting somehow doesn't affect it. I mean, right? We cut along the cycle, it just doesn't intersect n. So we can expect that when we cut, let me erase something here. Our surface will become something like this. And the Greek holonomy is still over here. And we can draw same type of pictures. So let me try to do that. So I've drawn them in yellow before. All right. So this is the black-white graph, as I usually draw that in yellow. The corresponding triangles would be over here. So what we see over here is just kind of a universal cover of a self-folded triangle, right? Our holonomy n is now just holonomy from one side, from kind of one metal domain to the other, and we can right. Sorry. Let me correct this picture. Right. And our holonomy n should be calculated as a measurement matrix of that guy, right? But if we just take matrix elements of n and apply them to this eigenfunction for our operator, what will happen with matrix n? So it will be matrix n prime, which will become just 1 lambda plus lambda inverse 0, 1, right? So how can we see this matrix? How can we see this this measurement matrix in our picture? Well, that all works if we put lambda inverse here, lambda square here, and lambda inverse here, right? So in other words, I'm just saying that we can take the Fock-Goncharov recipe for this self-folded triangle, take the corresponding quantum cluster algebra. If it's SL2, it will have just two commuting variables. And we can write a representation of these two commuting variables, one x by lambda square, another by lambda inverse, and then matrix n, after applying its coefficients to the eigenfunction, will become just the path count, the measurement matrix for this graph. Fine, but now the last thing I wanted to say is that's good, but what if we now try to do the same for the matrix that actually crosses our cycle through which we wanted to cut? Let's see what happens there. So what do we expect from pictures? Well, from pictures, we somehow expect that there will be some way to write a holonomy that starts at the boundary and goes into puncture, and then on this one can start the puncture and goes to the boundary, which doesn't make any sense, to be honest. But let's try to make sense of it. Oops, sorry. And well, let's just see what happens to the matrix M when we apply its matrix coefficients to our function psi. What happens is the following. So the matrix M indeed factors into two factors, and I'll just write one of the factors for you, and this factor is lambda to the power 1/2, d to the power 1/2, and then matrix like this. 1 over lambda minus lambda inverse d, lambda inverse over lambda minus lambda inverse d, lambda inverse 1, where d is the kind of canonical variable to lambda. So d lambda equals q squared lambda d. Now, question is, can we see this matrix in a picture like that? Well, the answer is, in fact, yes, we can. And here's how you do that. Let me just redraw that once again, one last time. So if this is our entry points and this is our exit points, then and our weights are as before, so we have lambda squares over here, lambda inverses over here. We can try to calculate the measurement matrix, an infinite one, from here to the infinity. And indeed, if we do that, we will almost succeed. So what will happen? We just need to take these denominators, write them as power series. And indeed, we see that we get power series. So there's just one path from 2 to 2. But there are, so here we have just one summoned. But we have infinitely many paths from 2 to 1, for example. 1, another one, and so on. So that will give us infinite series. From 1 to 1, again, infinite series. And from 1 to 2, again, just one path, which is precisely lambda inverse. Right? The problem is that if we take a path from 1 to 1, we see that somehow this path has infinite weight, right? Just because the weight of this path is this variable over here to power infinity. So it's kind of lambda squared to power infinity, which doesn't make sense, unfortunately. But on the other hand, if we just can do the renormalization, yes, I'm not sure I'm allowed to use this word, but still, if we kind of pretend that all of this region over here, we just put a placeholder d and see how this region commutes, how how this region kind of Poisson commutes with other phase variables, that will commute precisely as the d should commute over here. Right? Right. So what we do now is we just say, okay, fine. Of course, taking infinite products doesn't make much sense, right? But what we can do, we can just replace this d with some extra frozen variable, which will have exactly the same frozen x variable, which will have exactly the same commutation relations with everything else as such a region over here. And now, finally, let me just draw one last picture to show how these frozen variables look like, say for SL3. I have 1 minute. 1 minute warning. Fine. Will be enough to draw a picture, I hope. Let me just draw that for SL3. So if this is a puncture somewhere in our surface, this is a triangle, so maybe we'll have some other stuff as well. Let's say we're in PGL3. So this is our cluster cover. How we add these extra frozen variables is as follows. We, again, recover our bipartite graph. Remember, these variables, they somehow should come from this infinite paths around our puncture. And these infinite paths, they end somewhere. So let's say one of the paths ends over here. It then takes all of this region on the universal cover, and say another path ends maybe over here and takes all of this region. Right? For each of these paths, we'll add an extra frozen variable, and the rule we added will be as follows. So we'll add one frozen variable corresponding to this green path, And here how it will go. So you see this boundary edge kind of is marking the end of this path. So it has two faces on kind of side of it and two faces on the kind of, vertices. So we draw outgoing arrows to these two faces and incoming from these two. Then we had another frozen for that guy. Same rule. Put some yeah, kind of dash arrow between those. So right, and well, I guess that's the end.
Questions in the room?
There appear to be no questions in the room at the moment.
Does anyone have a question in Zoom? It appears not to be. Let's thank Alexander again.